when I talk in my institute, I talk to my atmosphere guys, and then I realized that their concept of a terrestrial planet is not the same as my concept of a terrestrial planet. So we needed to get together and agree amongst ourselves what we call a terrestrial planet. Just to outline that, to the atmosphere scientist, it is a planet with an Earth-like atmosphere. So Venus, Mars, and Mercury would not qualify, for an atmosphere scientist to be a Earth-like planet. Or they say Earth-like more than terrestrial, but Titan may. Titan has an atmosphere that is, from the chemistry, kind of similar, to the Earth atmosphere with the nitrogen in it and so forth. I think Titan is significantly different from the Earth otherwise, but that's interesting to note. The geoscientists, to which I count myself, it is a planet composed mostly of rock and iron. So you have an iron core, you have a rocky mantle, you have the crust, and all the geology on it and so forth. So Venus, Mars, and Mercury certainly qualify. But what about the Moon and Io and Ganymede? These are not planets according to the IAU definition, which is another complication in there because they're not planets. I don't think we need to spend much time in going into the definition of what a planet is. Actually, you can pick that up from the web and just decide for yourself whether you find that agreeable or not. I mean, there are people that have problems with it and others with not. To me, I mean, what is important for what we're discussing here is that these are almost entirely rocky, and iron bodies. So they are composed of a iron core and a rocky mantle, and this is the physics what we're looking at. And they may have an ice layer on top of it, So that's fine. The ice layer is okay, or the ocean or whatever. But and therefore we discriminate that from the gaseous planets that are have that gaseous envelope. Actually, just to pick up on that, Francis, there isn't. I mean, I was speaking about the giant planets having these big cores, from the point of view of those who do the accretion modeling. But if you come from another perspective, if you look at it from modeling the geophysical properties or the physical properties of these planets, you're not required to give them a big rocky rock iron core. You can actually model Jupiter entirely, that's extreme, but entirely without a rocky core. So it is not clear, that that Jupiter has a 10 Earth mass core. It's not entirely clear. I mean, the data do not require that. I mean, you can form it by having this big core and collapsing the gas on it. But maybe in 10 years' time, some clever guy someone amongst you, comes up with a model to build a Jupiter without that. I don't know, but from the perspective of the interior modeling, it is not required to have a substantial rock face in these things. Now, Francis may argue from a cosmochemical point otherwise, but I'm just putting it from the angle of the physics of these bodies. Okay, so the exoplanets have provided us with a new samples of planets and planetary systems. Most of this discovered rocky objects to date, fall in this class, super-Earth and mega-Earth. And that, of course, is a bias, that comes from the observations. I mean, that doesn't say that, other planetary systems have nothing, rocky other than super-Earth and mega-Earth. There may be smaller planets in there, but it is just a bias in our detection capabilities. I mean, there have been claims now to having discovered, I think there's still candidates of that are Mars-sized, down to Mars size, But that need to be confirmed and so forth and so forth. Okay. What are we doing with these terrestrial planets? I mean, people like myself and others, they try to understand them from they apply a theory from a physical point of view. And I have to say that this is mostly thermodynamics, what you're doing with them. So you look at the interior structure, you try to understand, whether they have an iron-rich core, rocky mantle crust, phase transitions, chemical layerings, and the variations with steps of thermodynamic and transport variables. So, thermodynamics, transport theory, this is the kind of stuff that you're using to study these things. Then interior dynamics, core and mantle convection, heat transfer, volcanism, that's the expression on the surface or near surface, tectonism or tectonics better, magnetic field generation. This of course brings in the electrohydromagnetic parts, rotation and tides, tidal dissipation, but also if you look at the atmosphere, then seasons, evolution from the accretion to differentiation, core formation, outgassing, and then cooling, and by cooling, then providing work, deformational work, that then gets you the topography and all the nice geology that you can look at. And then, of course, habitability and life, and the question, is there a feedback to planetary evolution? Now, important elements of the theory are thermodynamic properties. So when you model planets, you usually are concerned with looking at density, or the thermodynamicists would say specific volume, but that's the same thing. Temperature, pressure, the composition, and how the composition affects then, for instance, transport variables. Chemical reactions can be of importance, although geophysicists often, leave them to the geochemists, and that's often done. Phase transformations. Then we have energy sources that power the machine. Accretion. So there is, when you form the planet, there is energy deposited in it. If you start out with a small thing and then you rain stuff on it, then the kinetic energy that is turned into potential energy is dissipated as heat, on the planet, and you heat it. Radioactive decay is a very important element. We've already seen aluminum 26 at work. We're not really looked at iron 60, but these are soon gone, and the planet is left with these guys here, uranium, thorium, and potassium, to heat it. And one of the big debates, that is still ongoing, I think, is just how much of it is powering the energy balance of the Earth and other planets. Is it is like in the old days, in the very old days, people believed that the heat flow out of the Earth was in equilibrium with the radioactive decay, and that you could calculate the concentration of radioactive elements by looking at the contributions per unit mass, and then balance that with the heat flux out of the Earth. And here you have your radioactive heating rate. But we've learned in the 80s, I think, it was that cooling, was an important contribution to the energy balance, and that the radioactive decay could not balance the heat flow entirely, and just how much of it is still a matter of debate. Transport properties, viscosity, we will encounter the temperature and pressure and volatile dependent viscosity a few times during the remainder of this talk. It's basically the most important quantity, that sort of determines, how a terrestrial planet evolves is the viscosity of the mantle and to a lesser extent the viscosity of the core. Thermal conductivity, porosity may matter, although not in the bigger things. That is you know, if you look at small planetesimals and small bodies in the asteroid belt, for instance, that would not qualify actually as a planetary body. Porosity may matter. It also matters, you know, in near surface layers, for instance, the regolith of the moon or in Mars, but not in the deeper interior. Electric conductivity is an important element, you know, that needs to be considered. Now, the basic understanding of at least people like myself have of a planet is that we look at it as a heat engine. What it basically does is it converts thermal energy into gravitational, deformational, and magnetic field energy. So, you know, when convection, you know, brings material, you know, up, you know, you can in-place it, and when it then cools, it has a potential energy surplus with respect to its surroundings. You can deform a mountain belt, you know, and form the Alps, you know, and perform deformational work, or you form Olympus Mons on Mars, for instance, and you produce a magnetic field. But the observation is that this engine is an integral part of a more complex system, and I try to outline this here on the side to the right. So when we look at near-surface processes, we have the Earth's crust, we have the atmosphere, and there is interaction between the atmosphere and the crust, I mean, through and the hydrosphere through erosion, for instance, and similar processes. There is an effect, a clear effect of the biosphere in this circle, because the biosphere is working at the evolution of the atmosphere, and also, you know, has its effect on the hydrosphere and on the crust. So that circle is, you know, relatively clearly understood in a way. But then we go deeper and we put the mantle into there. And then we have the volcanism feeding the crust, the evolution of the crust. We also have the mantle degassing and feeding the atmosphere. It may be the most important process in forming the secondary atmosphere after the first, you know, accretionary atmosphere is gone. So there is this interaction. But then, you know, if you have plate tectonics, and this is this thing down here, and I assume that, you know, you all have at least heard about plate tectonics before, but still, let me just say that with plate tectonics, you form at so-called mid-oceanic ridges, you form new crust, you move it to the side by the pressure that is exerted on it, on the formation, on the drag that is exerted by the flow of the mantle, the convection of the mantle underneath. You move it until the plate collapses and it sinks into the interior. And then deep in the interior, you close the circle, and then you know, have this machine going on. And this machine, this is basically the machine that you know, creates the volcanism that pushes you know, parts of the crust to the side, and, you know, is at the heart of folding up mountains. That drags water into it, you know, that is in the hydrosphere, and that creates new continental material at subduction zones and so forth. So the closing of this circle between the crust and the mantle is an important element of the tectonics of the Earth and the working of the Earth. Now, on Mars, we believe that this is not closed. So on Mars, you don't have that. On Mars, there is a plate that is on top of it. There is volcanic activity, you know, or has been, or has, yeah, volcanic activity for some time, Olympus Mons here, and you may put some volcanic load on it and then maybe erode the crust from underneath, but you do not have that efficient cycling that you have here, stuff that comes up, takes stuff from these other reservoirs and brings them back in, and closes this cycle here. So that is the element of plate tectonics. Now, plate tectonics is an interesting thing. I mean, plate tectonics is in a way similar to terrestrial planet, depending on who you talk to. I mean, if you talk to somebody who's making his living from being a tectonics expert, he will say that plate tectonics has certain things that are required. For instance, the stiffness of this plate, that this plate moves laterally in a stiff fashion, or other things. I'm not an expert in that, but I won't go into much detail. Or for the geologist, the rock suit that defines these margins is an important element of that. For the theoretical planetary geophysicist, it's not that important that this thing is a plate. I mean, the important thing is that you bring this stuff into the interior and move things about. So from theoretical planetary geophysicists also know what they call mobile lid convection. So this is a mobile lid, and on the mobile lid we don't have any requirements on being stiff or something like that. We only have the requirement that we're moving things about, and so in a way, I mean, that would suffice our requirements, at least from this perspective. There may be other perspectives where it becomes important again, but from the perspective of this talk, I mean, I wouldn't really care whether you have it as a plate or a mobile lid or whatever. Anyway, so that is what I wanted to say about that. Now, this putting down this cold stuff in here is like stirring your pot on your surface. I mean, on your oven. And what it does is it enhances convective cooling. And I will show you later an image where you see that you are moving you're operating your convective cooling between a higher temperature as in other competing models. So temperature difference. So you have this cold stuff that is put in here. And now the increased conductive cooling cools the core here. And when you cool the core, you drive the dynamo that generates the magnetic field in there. Maybe, no, this is not. And the dynamo action then creates a magnetosphere that at least shields the whole thing from part of the, the not the nice things that come with the solar wind. But then, of course, you have you have other things here that of course endangers this system. So the whole thing is an intricate system that needs attention, and I'm not sure that anybody has come up with the whole description of it, but parts of it are then, of course, subject of studies and theoretical modeling. Now, I said that we're interested also in the other the other terrestrial-like planets around other solar systems. And here's just a quick summary of what we know. We know that mostly we know the Jupiter-like planets. I mean, there are some Uranus and Neptune-like planets, and there are a few Earth-like or rocky planets that that we know and that we have mass and radius of, so that we can actually tell it has the density of something that needs to be explained by rock and iron. And here is a chart that has density, and that's why they are there, because they have been observed both in the radial velocity method as well as in the transit method and the mass. And here is a collection of planets, and you see that there is, I mean, usually what we're having in the exoplanet community is a disjunct set of values. I mean, you have the blue ones that are the radial velocity method detections, and then the transit detections. And we don't care too much about, you know, what is plotted here. I mean, it's the magnitude of you know, the star which they orbit. But to note that they are disjunct. And what we actually would like to have is that, because with the radial velocity method, you're getting the mass. And with the transit method, you're getting the radius. And we would like them to coincide such that we have a lot of planets from which we know both the mass and the radius, and therefore the density, and therefore the chemistry. And this is something that actually the Plato mission will do. I mean, Plato will detect and observe planets in that regime, there where the radial velocity, you know, planets are, and thereby give us thousands of planets that we would then have a mass and a radius, so we can do some geophysics or planetary physics with them. So what are people like myself, why are we interested in exoplanets? I mean, given the fact that up to now we don't have too much information about them. Well, you know, this is a paper by Latham et al., who's been looking at the chances, I have to say chances of small planets. So there seem to be a lot, so hopefully that is true. But what's also interesting is that you know, the systems themselves, and I alluded to that during my talk a lot of the times, that we find systems where the giant planets are much closer than Mercury in our system, and we were wondering about the habitability of these systems. And we also are puzzled, you know, by this thing here, that the orbital eccentricities vary so much, as well as, I think, the inclinations. So that is something that is puzzling, because in our solar system, we're basically down here. We have very small eccentricities and very regular orbits, you know. And you know, if the eccentricity varies as in these other systems, there is the chance for dynamical instabilities. You know, in the previous half of my talk, you know, we've seen these instabilities, and they're usually coupled to eccentricity variations. So that can be a problem. Another thing is that we're interested in is this thing here that I took from an old paper by Russell in the 1930s. Who's looked at the maximum radius that a planet can actually have, and derived this formula for the critical pressure in the center of it, tied to the molecular number. And what you have is actually that a planet cannot grow to a you know, any size, but there will at some point, you know, it goes into in the Brown trough regime, and then it decreases that. Now, in our solar system, we have Jupiter and Saturn pretty close to this maximum, about somewhere out here. But the terrestrial planets are down here, and it would be, of course, interesting to get planets that are closer, you know, to this maximum value in other systems. So that's an interest. Here's a paper, here's a chart from Guillot and Gautier, who's looking at that. You know, for a gaseous planet point of view, and also at hot Jupiters and how their atmosphere interacts with their host star, but we don't have much time to look into that. So, I mean, this is the radius-mass relation that people have come up with to explain exoplanets. You see the large variations of you know, the error bars, I mean, in the radius and mass determinations or estimates. And here is our solar system, and you see that with some of them we're getting, you know, upper here and into interesting regimes. You know, what is it's not in the legend here, but this is a planet that's basically made of ice, and this is a planet that is basically made of iron, and the Rockies are in between. And you see that some of these planets, at least, you know, if you can take their values at face value, that require substantial, you know, water components, you know, to explain their densities. So, I mean, this is this opens up, you know, a whole new set of parameters for the theoretical geophysicist to study. And then there are some that, you know, cannot really explained with these models. So what is happening here is a a Uranus type thing or whatever. Now, here's another look at this, though. What I'm saying is that terrestrial planets are relatively well understood, although, Earth plate tectonics still poses questions. Pressure and compression are relatively low, much smaller than the critical pressure for degenerating into Fermi gas. This is what defines this maximum here. We have the advantage of that the pressure range is largely accessible actually to experiment for the terrestrial planets. I mean, the diamond anvil cells, you can get up to ranges that would correspond to the lower mantle and maybe even core pressures, although I'm not quite certain about that at the moment. So the pressure range is accessible, while the rock rheology is highly nonlinear and complex, there is still a way that we can actually think that we can handle it and come up with models like Mars. Now, if you compare a super Earth with that, then you would say that the pressure range in the Earth covers only the outer shell of a 10 megaearth super Earth. So if that is the Earth, then the Earth mantle corresponds to this little bit of the outer shell of the super Earth. For instance, the post-perovskite phase that has been much talked about for the lowermost Earth mantle is not very well studied, but there's a lot of activity going on here. Is pretty close to the surface in a super Earth. There may be more phase transformations that we don't know about, no, this is the post-perovskite phase, I'm sorry, that we don't know about on the Earth that would determine the properties of the deep interior. It is actually not clear, and this is of course something for the chemist, that there's actually an iron core, or whether or not iron and rock may dissolve into each other, and that there is no clear separation between a core and a mantle in a super Earth. That is, of course, very speculative, but we can think about these things. And also, this is from a work that Vlada Stamenkovic and Doris Breuer and I published a few years ago, where we did models of super Earth and their thermodynamics. We were pointing out, how you have to extrapolate. So this is something that is covered, by experiment and relatively well understood theory for a terrestrial planet. And this is where you end up in the center of or the core mantle boundary of a 10 Earth mass super Earth at a terapascal. And you see that what we're doing is, this is amazing, how we extrapolate that. And this is, of course, very dangerous if you do these things. So we need a much better understanding of what is going on here. We're at the moment, we are formulating a research project, together with guys who do first principle calculations of equations of state, in order to see that we get a better handle on this. But this is a very demanding task. Okay, geophysicists at least, try to understand the properties of planets from a very simplistic chemical component model. So we're modeling them by considering a gas component that is consisting of hydrogen and helium. Then we have what we call the ices, although this is not necessarily in a solid form. Ammonia, methane, and water. And here you see a ice mantle, so to speak, the ice layer of Ganymede. But this is an ice, this is ice too. This is Uranus and its gaseous envelope. And then there is the rock iron component. And from the material properties of these, we're then, for instance, making models of the evolution of Ganymede by coupling what we believe about the transit properties of the ice with that of the rock, and then we're looking at how to explain the magnetic field of Ganymede, just as one idea. I think we can skip that, and this is another super Earth discussion which we don't need for this time. So, but this is an interesting, at least I find this an interesting diagram, and I think it was first put forward by Dave Stevenson, and I call it Dave Stevenson's Toblerone diagram. And it considers these three components, ice, rock, and gas, and it postulates that you can actually, popularize this whole space that is, made up of that. And I don't know if you really can do that, but anyways, what you see is that in our present solar system, you're basically at the edges only of it. So you have the Earth, which is basically a rock thing. You have Jupiter, that is basically a gas planet, and you have the ice moons that are sort of in between. I mean, the ice component, rock, right down here. But in principle, one could think that one could have many more variants of this, and might detect them, in other planetary systems. Okay, now coming back to our solar system, let me just briefly introduce some of the physical properties of the planets in our solar system. So the radius normalized to the Earth, so you see they're all in the same ballpark of sizes between, for the Moon, the smallest, about a third to the Earth, and Io is about as big as the Moon, and Venus is big as the Earth, and so forth. We have a variety of masses. That is, of course, much more larger than that, because that depends on the power of 3 of the radius. Therefore, we have a larger variation here. Interestingly, the density is relatively similar, but even more so when you remove the pressure effect, the compression effect on these densities. And then you find that Venus and Earth are in that ballpark. Mars is not too much away from it. The Moon is lighter. Ganymede, with its large ice component, is much lighter. Io is a bit lighter, but falling in the smaller part of these terrestrial planets. And Mercury, of course, sticks out. Mercury is very dense, and the simple explanation is that Mercury just has a lot of iron, and that is reflected in the size of the iron core that it is associated with, of 0.8. I think that number still holds from the messenger data, while otherwise, a value around of about half of the radius is more common. Now, there is, of course, the exception of the Moon, that has a very small radius. Ganymede, if you take away the ice component, then you would still have about half, and Io is again in this ballpark. So a core radius that is about half the planetary radius seems to be pretty much representative of a rock iron thing, and if you add a substantial ice component to it, then of course it's about a third, and a third. I should also note, and I will use that later, that there are magnetic properties. So we have the Earth having a that's-generated magnetic field. Venus doesn't have one. I mean, there's an upper bound to the magnetic moment. Same for Mars. I mean, it has crustal magnetization. We know that, so it once had a magnetic field. The Moon also once had a magnetic field. Ganymede does have a small one, and Mercury does have a small one. So we have the magnetized bodies, that is today Mercury, Earth, and Ganymede, that we need to explain, and I won't go into Ganymede, I don't have the time for that. And we have those that once had a magnetic field, Moon and Mars. And you know, some of us, including myself, believe that Venus also once had a magnetic field, but we cannot prove that, at least at the present time. A quick look at Mercury and the surfaces of the planets, just to get you acquainted with. Now, this is Mercury. is basically a battered world. You know, here's the Messenger spacecraft, created, you know, similar way to the Moon. And not much of endogenic tectonic activity that formed the surface. Different from that is Venus. Now, Venus is in so far particular that it has this optically thick, massive atmosphere that does not allow us to look through, you know, with cameras on the spacecraft. So we explore Venus by looking at it with radar. You know, the radar gives us then, you know, the tectonics and the topography and so forth. You may wonder why this is so yellow. I mean, radar is, of course, black and white. Now, NASA, this is a NASA image. NASA has used the color that the Soviet lander had seen, so to speak, in their short lifetimes, you know, of the light on Venus, to use it to color their radar images. Now, there are interesting features on Venus, and that is it is dotted with volcanoes and with lava features that, you know, go a long ways, you know, from this volcano here down here into there and into this crater over there. Though there are lava channels that span thousands of kilometers on Venus, you know, suggesting that the viscosity of the lava is actually very low, and that is an interesting thing to consider. Of course, I think you know that the Venus is very hot, with a surface temperature of about 700 Kelvin. And here finally Mars, you know, with this desert-like planet with an average temperature of, what is it, minus 60 degrees centigrade. Major volcanoes, a major graben system, you know, in a way, I mean, the conditions are not so much removed from habitable, not as much as Venus. And of course, I mean, Mars is our role model of a planet that does not have plate tectonics, as we will look at later. Here is the spacecraft Mars Express, European spacecraft with our camera on it that produces these stripes, and we can, it's a stereo camera, so we can, you know, produce all nice pictures and flies across the surface. We also have rovers on there, so Mars is certainly the planet that has been best explored of all other terrestrial planets or other planets in the solar system, including, I mean, this laser altimeter picture that clearly shows the dichotomy of it with the Tharsis province, a volcanic, super volcanic province with the graben that we saw here, those big volcanoes. You know, people have thought that this looks a little bit like a mountain chain on a subduction zone on the Earth, and Norman Sleep has discussed that to some extent, but the consensus today is that Mars does not have plate tectonics, but it has an old surface dotted with craters and a surface that looks much younger, although when you look at the gravity field, you see that the surface